Görebilir misin? Hayır.
Okay, so hello everyone. Welcome to Sabancı University Science Student Chapter's second Popular Science event. Today our guest is Professor Durmuş Demir. At the beginning, I would like to talk briefly about SciAm, who are we and what are we doing here. I hope everybody can hear me. Okay. SciAm is actually an American math society, which is generally focused on applied mathematics and industrial mathematics. And here, Sabancı University Science Student Chapter is two student chapter in Turkey. One of the two student chapters in Turkey. One of them is in Metro and the other one is here. Here actually, we are a relatively young student club. It's been just a year. But we are organizing different kind of events, from math to computer science, and from computer science to this kind of physics and more general science events. If you are interested, at the end of the event, you can join our email groups and also WhatsApp group. That's all from me. Actually, I don't want to talk much, Professor.
We are tired a little bit. This is evening time. So I'd like to talk about, let's say, a little bit, say, heavy topic, but I will try to make life as easy as possible for you. So I'll try to follow basic mathematics and basic ideas, for not to complicate things for you. So I'm going to talk about black holes and particles around. What I will do is to first make an introduction, okay? At the level of, let's say, undergrad or let's say grad students, more or less, and then try to motivate research with black holes in terms of the particles around the black holes. And then I will try to motivate with another topic, which is more, let's say, which is closer to my research topic itself. And then we will see all together what these black holes can give us in terms of the particles emitted or, let's say, scattered. When I say flat space, please take in mind, take into account the figure on the left. When I say curved space, you can imagine a terrain like this, okay? So there is a flat terrain on the left, and there is, let's say, a rough terrain on the right. And this is a figure, it's not exacting, but this is not correct to tell you always, but at least for understanding basic concepts, it makes sense to have something in mind, and it's something you can keep in mind in that. Let's start with flat space. So I introduce flat space. Imagine two infinitesimal closed points, and these points are separated from each other by this blue rod. Okay, blue stick, whatever it is. It's a very, very short one. So you use Pythagoras theorem to calculate length of the length of this blue thing, ds. And as you already know, ds squared equals dx squared plus dy squared plus dz squared. There's nothing surprising with this, and this is known for some time, like more than 2,000 years. So the point is that if the two events separated by this blue rod coincide, it can only if the distance between them is z. That's the whole idea. So this is what space is. Now let's look at space-time. Not space, but time. No, time is added. Adding time is not easy because we cannot imagine 4 dimensions. But you can imagine something like bringing down an additional axis, red axis, the time axis. Okay. you can ask yourself, well, isn't this a trivial thing? Well, normally, yeah, but when you look at the distance between 2 points, when you include time, you see that s squared is equal to now the old dx squared plus dy squared plus dz squared part plus a term like this. This added term is negative. Is negative. Time comes with a negative sign in front. And this is required for light to propagate in universe. If it is plus, then light never propagates in this universe. This is something necessary. So this minus sign is required, okay? And this is something that makes 4 dimensions very much different from what you would have in play in 3 dimensions, from the 3-dimensional world. So this is our 4-dimensional world. And what is interesting is that, well, the 2 points may be separate, they may not be coinciding, but the distance between them could be 0. Okay? In fact, what light is following the points between which the distance is 0 always. So light, here there is light, okay, at this point, it travels to that point, and the distance between these 2 points is 0. Okay? That's the definition. That's what light is. Okay. If this ds squared is negative, then that's called matter. If this ds squared is positive, then that's called as tachyons. So matter, entire material existence can be classified by this relationship ds squared. That's it. So this is what Einstein introduced into science via relativity. Okay. Special relativity, but we will, of course, generalize this whole thing to general relativity in a moment. So this is flat space-time. Well, I mean, you can change coordinates. You can say that, Durmuş, I don't like x, y, z. I want to change it to radius r, polar angle theta, azimuthal angle phi, and you can write it in that way. Coordinate change never changes physics. The physics is the same. So nothing has changed. It is still flat space-time. Okay? So nothing has changed. But now, imagine that you are in a regional space-time. You are in a regional space-time where there is some kind of an intrinsic speed in the system, intrinsic velocity in the system. Okay? In that case, what happens is that time part is multiplied by this green term, and space part is divided by this green term. This intrinsic velocity or intrinsic speed is something that is special to the system, okay? Well, you can imagine anything, but we will imagine one particular example concerning this. What happens here is that essentially this is kind of a coordinate transformation where there is a new physical variable being involved in the transformation, and there is a dilated time and contracted space in the game. So there is a kind of dilation or contraction, whatever. And if you think of what kind of speed can I have, what could it be that I have an intrinsic speed in the game? Well, that is perfectly the escape speed. Okay, imagine a coordinate system just as before, but in this case, just put at the origin a planet, for example, Jupiter. Okay, put Jupiter there, and now look at what is happening here. What we have to do, as I'm telling you over there, is to compute the escape velocity. I mean, what is the velocity or what is the speed with which I can escape from Jupiter? Okay, to do that, all you need to do is I'm sorry, this slide is not good, but anyways, you equate kinetic energy to potential energy from gravity, Newtonian gravity. You obtain just escape speed squared to be given by that expression. Now, in place of the intrinsic velocity or intrinsic speed, you can plug in escape velocity, and what you get is the distance, this distance. The difference is that compared to the previous page where we introduced that kind of arbitrary intrinsic speed, here what we have is that there is an escape velocity enters the distance between two space-time points around a given astrophysical object, let's say a planet or sun or something like here, like this place. The interesting thing is that this escape speed squared is given by Newton's constant Gn, the mass of the body over there, and the radius at which you are supposed to get out of the gravity of this object, whatever that radius is. Well, now let me show you what this escape speed squared is. Actually, the escape speed squared over speed of light squared is just this ratio, and from this ratio you compute a specific radius Rs. This ratio is equal to Rs over R, and Rs is given by the Newton's constant times mass of the body divided by speed of light squared. This is something intrinsic to the object, and all you have to do is to just rotate around the body until you get out of its gravity. If you wonder what this Rs is actually the gravitational radius of the object. Normally, when you look at it as a geometrical object, you see a certain radius R, but gravity doesn't see this. For gravity, what is seen is much smaller. For example, for gravity, Rs equals 3 kilometers for Sun. For Jupiter, it is 3 meters, and for Earth, it is 10 millimeters. Okay, for Earth. Could you imagine Earth's size is just 10 millimeters for gravity? Such a small little thing for gravity's action or interaction. Then we can write this everything in terms of this new variable, Rs over R, Rs over R. The point is that this Rs is a characteristic scale. It's a characteristic radius in the game. It has come from this, the escape speed by the definition of the escape speed. What is important is that depending on if R is larger than or smaller than Rs, you can have different physics. You can have different regimes of, let's say, distance ds squared. But that's all we are discussing here. Actually, this distance we got here, it is surprising, but it's actually the solution of the Einstein field equations, the equations of Einstein, written in 1915. In fact, this guy, Karl Schwarzschild, solved these equations in 1916, and he found a solution. And solution was this, okay? We found this solution from geometry. We found this solution using geometrical arguments and intrinsic speed type concept, okay? Just to make life easy for us. You know, I mean, I cannot write down Einstein equations here and solve it for you. It's not feasible. It's not for you. It's not that much, how to say, at least mathematically complicated. So this is Einstein's theory. This volume integral gives you Einstein's equations. Here we know it is known as vacuum energy. I set it to 0 and I find this solution. This is known as Schwarzschild solution. The point is that, well, when you can have that ds squared, but then you have to characterize the system. What is the nature of the system? What is happening here? To characterize that, you gotta check the system, and one thing you can check is the curvature of the space-time defined by this ds squared. You keep in mind that this ds squared is essentially what characterizes your space-time. It's the Gaussian distance between any given points, and it gives you entire intrinsic curvature of the manifold on which you are living. Let me not get into the technical language, but whatever, the Riemann curvature square gives you 12 Rs squared over R to the power of 6. And this object is infinity as when R equals 0. This means that the curvature is infinitely large at the origin, and it decreases as you go farther away from the object. This infinite curvature is a signature of black hole. Okay, but we will define it much better. No, let's define it. Okay, let's define what is black hole. I mean, what do we mean by black hole? Can we have always a black hole around? That's important. If a body M is too massive to require an escape speed bigger than the speed of light, then a black hole forms. Okay, so if escape speed from the object, from the astrophysical object, is greater than speed of light, then that object is a black hole. Okay, because escape velocity greater than c means radius is less than the Schwarzschild radius Rs. It is the same meaning. This means that you are within the object essentially. When R equals Rs, you are at the event when R equals Rs, you are at the event horizon. This is known as event horizon of the black hole. There is a critical radius R equal to Rs, at which and this is the horizon. That is to say, it is the point of no return. When you approach this point, then you will never come back from the black. That's the whole idea. This Rs is this. Then at R equals Rs, you have infinitely slowly passage of time is infinitely slow. Okay, you go there and you just stay there essentially. If you are within the black hole, okay, then the point is that since that's a point of no return, you cannot probe what's going on inside the black hole from external observations using. You don't know what's happening within the black hole. When R is less than Rs, black hole interior is effectively time and radial distance interchanged. Essentially, time is imaginary within the black hole thing. At least for this Schwarzschild structure, the simplest structure I am showing you. This is very simple. I mean, this is the simplest geometry you can imagine. And I'll explain all basic concepts with this one before going to a little bit more complicated stuff. So let's look at how the photons are moving around the black hole. Okay. For this, we use the basic definition, ds squared is 0 for photon. Then azimuthal angle can be, we can go to the azimuthal plane. We use conservation of energy, we use conservation angular momentum, and then we obtain an effective potential down there, this blue one. Okay. This effective potential tells you the potential seen by the photon. Could you imagine photon sees a potential for itself? This is important. This potential will tell us that photon behaves in as if a planet is rotating around the sun. That's the motion of the photon. Now let's look at this. S squared equals 0 gives you this relation. Equation of motion gives you this relation. If you equate them, you find the critical radius RPH. RPH is 3Rs over 2, and this is the radius at which you have a stable photon sphere. Photons are revolving around the black hole at a distance RPH, and they remain there as stable. This is the smallest stable radius for an object revolving around the black hole. This is the critical radius. At this point, you have a photon sphere, you have a stable sphere of photons. You see a shining photons from this. As you see, the event horizon, the critical radius, the point of no return was here. But the photon sphere is not equal to that. It is far away. Let's say 1.5 times bigger than that one. This means that in this region, in this gray region, you can still get into the black hole. You cannot escape. So essentially, size of the black hole is set not by the event horizon, the critical radius are equal in Rs, but essentially the photon radius, of course, you have to take into account lensing of the light under gravity, which is important. I will tell you about that. Okay. This is the last stable orbit. It depends on the underlying gravity theory. Here in the simple case, it is like this, but in more general cases, you have different structures. Let me give you an example. This is the supermassive black hole in the galaxy M87. Okay, it's a neighboring, it's in the Magellanic Cloud. I mean, it's a neighboring place for us. Okay, and there is a galaxy. At the center of the galaxy, there is a black hole. This black hole has a mass something like 6.54 billion times larger than the sun's mass. Okay. 6.54 billion times bigger than the sun's mass. Such a huge mass. And its event horizon is 258 times, 458 times the astronomical unit. Astronomical unit is 150,000 kilometers between the Earth and the Sun. This is the standard distance. It is something like this much larger. And here you see, this is just a picture taken, essentially. This is the event horizon like this, okay? I mean, they are able to see what this object is when you look at it, precisely. And we can, the point is that we are not just making observations for fun. We are deriving physical results from these observations. We are testing our models. We are using black holes as a laboratory. Okay, that's really important for our purpose. Black hole shadow. As you see, let me show you just as a shape. Okay, not too much mathematics. What happens is that, could you imagine there are these blue rays, there is this orange rays and red rays. As you see, the blue rays just go into the black hole, because their distance is smaller than this essentially the photon rays. They are captured by the gravity of the black hole. But there are this red ray is the critical one. It barely passes by the black hole. So there is a shadow seen. The shadow is not the geometrical shadow here. It is much bigger. So in a world of black holes, an artist, a painter would draw black hole not as a simple geometrical object, but as a bigger object, because object has a bigger shadow. Shadow size is much bigger due to this capturing of the light. Okay, light is not able to escape from the structure. If you define such a thing, the shadow is something like this, depending on the observer's position, depending on the Schwarzschild radius. This is the distant, this is the angle for the distant observer. And we are using these to test our models. Let me show you with a different picture. As you see, there are gray lines, dark gray lines. The light gray lines and the red lines, as you see. The light is coming towards the black hole. Black hole is just capturing them. RS is the event horizon Schwarzschild radius, and this yellow arrow is the photon radius, essentially. And of course, you can take a picture of this. This is the famous picture of the black hole picture. By using many terrestrial, telescopes, X-ray and all different ranges of telescopes. They collected data, they mapped data together, they formed such a picture, and they have shown this is shadow of the black hole, this dark region. The light thing around is actually light coming from the accreting matter. There is matter inflowing towards the black hole, but the matter is not inflowing on the black hole. It's just revolving around the black hole, and due to this accelerated motion, there is X-ray emission, light emission, and that emission is observed by the Event Horizon Telescope. Okay? This is Sagittarius A star black hole, another supermassive black hole. Of course, we can use AI techniques. Artificial intelligence allows you to eliminate many unwanted features. For example, the picture on the left was the picture in 2019, where they collect data and form this thing. But in 2023, they obtained such a, let's say, a clearer picture of the black hole by using AI. The same group of people did this. It's interesting that AI is helping to identify the region. As you see, this is the accreting matter around the black hole. Now we see the shadow region much better, and all details are clear now. Of course, in the future, we will have more and more sophisticated observations, and we will clearly identify many different properties of black holes like this. But at least at the moment, AI is helping us to eliminate all those, let's say, blurry parts. Light is banded by black holes. Maybe you remember from these stories of Albert Einstein. There was this guy Eddington who observed the bending of the light around the sun. Well, if it happens around sun, it happens very well around the black holes. What happens is that there is a real star over there, and light is supposed to go in an efficient direction in that way, but light is bent by the black hole, so observer there sees an apparent star over there. That's the idea, essentially. You can calculate this just using the photon motion equations, You can calculate such a bending angle, and this angle asymptotes to this value twice the Schwarzschild radius divided by the R0. R0 is the point of closest approach. The point is that this is the effective potential. Light is coming from the infinity, but it is getting reflected back. Okay, this R0 is the turning point. It is the closest point. It's coming towards the black hole. If it had larger, higher energy, it would of course come towards the black hole. It depends on its potential. It depends on its dynamics, total energy. For example, this is yet another exaggerated picture. Here there is a galaxy, and there are light rays coming from this galaxy. For example, red one is revolving around the black hole 2 times, and it's going to the observer like this. An observer is creating infinite number of images of this star. This is known as gravitational lensing. Okay, there is a lens produced by the object. This is especially good with dark matter. In between the let's say black hole and between the observer we and the black hole, there's nothing when we look at it. But light is getting bent. Okay, there is this lensing effect. We immediately say that, okay, there is something in between which is not seen by light, which is not emitting light, but which is bending the light from the other object. So this is the way we are searching for dark matter in gravitational setting. Now let's look at this, effective potential. You remember, we derived this effective potential before for light, okay? Actually, you can derive it for other cases as well. For massive particles, it is this red curve. For massless particles like photon, it is the blue curve. For example, if your energy is just here, you have a circular trajectory. You have one radius, okay? If you are a little bit higher, then you have one radius here, one radius here. You have 2 radii. What you can do with these? You can have an elliptical trajectory, the short radius and large radius, essentially. That's why in solar system we have all these the elliptical trajectories. We seldom have a perfectly circular trajectory. It's not possible. Okay? It never happens because it requires a huge tuning here. Now let's look at this. The point is that there is this potential energy barrier. I mean, originally our particle is in the black hole. It is in this region. Here. And that's classically, macroscopically, there is no way to get out of this region. It's a crazy domain. But there is quantum physics. If quantum physics, quantum theory works in such a medium, in such an environment, then we have possibilities. What? Well, our quantum particles can tunnel through the potential energy barrier. And if they can tunnel through, then they can escape from the black hole, which is perfect. Let's see this, okay? I mean, and you know what? These particles tunneling through the barrier are observed as Hawking radiation. Okay? That is what we call as Hawking radiation in physics. Let me give you a simple calculation of this Hawking temperature. I mean, we can use elementary mathematics to calculate it. Time it takes to go to this from the equation of motion, which is effective potential is given. You have this relationship, plugging in numbers and just taking out, you obtain this expression. You are setting energy to the value at the turning point. Then you evaluate this integration using residue theorem, and you find phi times r times rs, and time has 2 values, plus and minus. There is this plus time passing and negative time, positive time, negative time. And when you plug in them here, you see that positive time corresponds to waves propagating outside, and negative time corresponds to waves coming inside. Okay, so for waves going outside, you have an emission probability going like exponential of 2 pi rs times energy E of the particle. For absorption, you have e to the power of plus 2 pi rs times energy of particle. Ratio of the emission to absorption gives you this ratio. From this black body spectrum, you immediately calculate temperature, and this is precisely the Hawking temperature. Okay. Of course, I could have used here quantum field theory, matter, antimatter rules, etc., but you wouldn't understand what's going on. At least in this picture, you are able to see that there is a tunneling over this effective potential energy barrier, and that's it. And the particles which are able to tunnel through the barrier, go out of the black hole domain, are seen as radiation, some radiation coming from the black hole. And this radiation is what they call Hawking radiation, essentially. I didn't calculate these, but I can give you the formulas. There is a power emission from black hole in this form. I didn't calculate these. This guy, Page, has calculated these things. These numbers are coming from him. There is an evaporation time for the black holes. Black holes are evaporating slowly, very, very slowly, because this is a quantum effect. Tunneling probability is very small, and it's very hard to get out of the black hole. But of course, you might be having more than one particle going out of the barrier, black hole. In this case, you some kind of accelerate the evaporation time. And it happens indeed. People have calculated such things. For example, they looked at emission of neutrinos, photons, and gravitons, gluons, etc. Well, each time they find a certain ratio for the emission time, but it's not bad. I mean, you can calculate. Actually, in this sense, since we are discussing particles around the black holes, essentially, what's happening is that by looking at the evaporation rate of the black hole, you can easily say if there are particles in nature which do not interact with us, if the particles are not interacting with us, they should. I mean, every particle must interact with gravity, but they may not be interacting with us through other forces. By looking at the evaporation rate of the black holes, you may be able to say, there are additional particles over there which are not interacting with us, but they are interacting through gravity. I found them. You can say this. If not today, in future, when you will have enough, let's say, precision to calculate, you can say, Durmuş, if there are these particles, how about its statistical thing? I mean, is it a statistical object? Yes, I mean, in classical physics, black hole is a, let's say, singularity domain, which means zero temperature, zero entropy, because there is no motion at all within black holes, okay? There is no kinetic thing. Temperature is the average kinetic energy of the particles in the medium, and there is nothing like that. There is nothing of that kind here. In quantum physics, however, black holes must have non-zero temperature and non-zero entropy, because quantum motion is always there. It happens. It exists, as we had just calculated. In fact, you can use first law of thermodynamics to write change in the energy is equal to heat, change in the heat. Heat equals the temperature times the entropy. The temperature is nothing but the Hawking temperature, just the one we had just calculated. And the change in the entropy here is given by area of the black hole divided by the Newton's constant. This is the Bekenstein calculation. What's important is that you have the same black hole. Suppose, and you have, let's say, many numbers of particles you put in the black hole as a volumetric structure. What is important is that entropy is proportional to the surface area, not the volume. This is known as holography. There is a hologram-like effect in nature. Mother Nature is something like there are many degrees of freedom within the black hole, but what you observe as something contributing to entropy is the area, not the volume. It is not proportional to the volume of the black hole. It's proportional to the surface area of the black hole at the Schwarzschild radius, here at least. This is known as holography. Even in string theory, idea was this. I mean, they said that gravity in volume should be proportional to the conformal field theory on the surface. This was the idea. Of course, it has proven nothing much compared to the physical, let's say, understanding of these forces, but still it was a very appealing idea. There was this smart guy who talked, this was his observation in one of his talks. And it has started a whole new, let's say, era. Now let me tell you about a little bit different thing, but actually it's not difficult, okay? I'm sure we will understand it easily. Let us think about a little bit charge conservation. You know, electric charge is conserved, huh? Otherwise, how would these cables work? How would your cell phones would work? It wouldn't be possible. So, to ensure conservation of electric charge, photon interactions with light, remain unchanged under this shift. This shift. Photon field goes to photon field plus a term ds, and your theory remains invariant. Interactions remain the same. So then nothing changes. This is one of the most fundamental symmetries of nature, without which you cannot conserve electric charge. It is a fundamental relationship. But if you look at nature, for example, uranium associates via the decay of neutrons into protons, electrons, and neutrinos like this. This is your neutron, it goes to proton, and it gives off anti-neutrinos and electrons. This is known as beta decay. There is also alpha decay, but it's not important, but it is. But the important thing is, since the time of 1930s, is that this decay is mediated by massive and charged particles. Okay, massive and charged photons. Photons having mass, photons having electric charge. A crazy case. But you know what? There is a problem. Since these guys are massive, the mass explicitly breaks your symmetry. V going to V plus ds symmetry is broken. This means that for such particles, electric charge conservation fails. You don't have any electric charge. And electric charge is not a conserved number. Of course, Mother Nature cannot have such a crazy thing. Everything is working properly, huh? Things are working. People understood in 1960s that, well, to restore the charge conservation, they said that we can replace this mass of this vector field V there, mass of the photon, massive photon there, by some scalar field phi. It doesn't matter what, and this becomes mv squared close to pi squared. This phi is what we call as God particle or Higgs particle. Okay, it is for this reason that Higgs particle it has been discovered. It's people found it already. It exists, and these guys contribute to this thing. Anderson, Higgs, Weinberg, Abdul Salam. People have contributed at different stages of this idea. This is a very, very fundamental idea. Imagine you have electromagnetic light is coming, but light particles are massive particles. Since they have mass, their interactions are now very short range. And beyond that, what's crazy is that this mass term explicitly breaks your symmetry. To restore charge conservation, you need such a trick, and this trick works in nature. Now let's look at things from a different point. Quantum fields can be understood only by a cutoff. That's to say, you have to have a maximal energy scale, and you have to cut everything at that scale. If your theory is not the theory of everything, you have to do this. If you have a theory of everything, then you don't have to do anything, but such a theory doesn't exist. Okay? String theory is a kind of, how to say, there is no apparent success. The UV cutoff that I'm mentioning over there breaks translation symmetry. I mean, you go a long time, and at some point you get a blockage because the translation symmetry is broken. Quantum rules generate masses in proportion to the UV cutoff. Photon, however, acquires a mass in proportion to the UV cutoff. Yes.
What is the meaning of UV?
Ultraviolet. UV light, like the UV light itself. I thought that UV is something common.
I just wanted to make sure that it doesn't mean something else.
No, yeah, it's the same thing. But photon acquires a mass, and whenever it acquires a mass, the symmetry gamma going to gamma plus ds is broken. This means that the electric charge conservation fails. This means that your theory is broken. But in nature, there is no such crazy thing. Everything is working properly. So what you have to do is to restore electric charge conservation by replacing mass of the particle or cutoff of the theory by a new field. This time it is curvature, not the Higgs field, but curvature. The reason is that curvature breaks translation symmetry as the cutoff itself does. And this leads you to symmetry restoring emergent gravity, or what I call as emergent gravity. And you can have such crazy diagrams in quantum field theory. You don't have to calculate any of these. These exist, and these can be calculated properly, order by order in perturbation. Don't worry. People have calculated them up to 9 rules, crazy rules. So, okay, simulation gravity is a new topic. It can be tested at particle colliders like CERN and HC. It can bring explanations for elusive particles like dark matter. It can be tested at strong gravity domains like black holes and early universe. It's a new thing. Even the referee was having a very hard time to getting into the details of the paper, my work. And he said that this paper is still difficult because its point of view is novel. However, that is to be expected for novel ideas. I mean, at the end, maybe he couldn't understand everything fully, but anyway, he allowed it. Now let me illustrate what happens to black holes in this model, at least by giving you some rough plots. Compared to Einstein's theory, we have no these additional terms. Okay, compared to Einstein's theory, green part, we have these purple part, which is the new added terms coming from this theory. CO here is a loop parameter, and it's proportional to number of bosons minus number of fermions in nature. Okay, you don't know what this number is because you don't know if all particles are interacting with us. And here, parameter alpha is something that parameterizes the vacuum energy of the system. And this is your Schwarzschild metric, but metric has this Schwarzschild structure, the original structure, plus this purple term coming from this model. Okay, and once you use this model, you can, for example, calculate what the metric function. I mean, you can look at the shape of this function. This function has this form. We calculated this and plotted for different values of the numbers. You can also look at a plane where one parameter is on one axis, the other parameter on the other axis, and classify the regions according to the existence or non-existence of a black hole solution. There are regions where there's black hole. There are regions where no black hole. We can find also these regions. We can find, for example, horizon. I mean, this is horizon. In this theory, things are more complicated compared to the previous one. And our horizon depends on parameter values and the constant CO I am giving you in this axis. As you see, there are different branches for horizon. You can have more than one black hole solution depending on the parameter range you are using. Also, you can have photon sphere. The radius of the photon sphere is different in this theory compared to the radial axis. Along the radial axis, your photon sphere's radius depends on all these parameters and has different shapes in different domains. And you know what? You can test these. Okay. Once you have observations, you can test these if these are realistic or not. You can have the effective potential. You remember we had this effective potential from which we calculated tunneling of the particles, etc. You can do it. You can do that effective potential in this theory as well. And effective potential has this form. Schwarzschild black hole, then other parameters are listed here. As you see, there is a whole range of values from, let's say, from numbers like -5 to +5, for example. It depends on the parameter values along the radial axis. You have this effective potential. Actually, effective potential must have this form. Otherwise, you cannot form a black hole. This region is the black hole. And there is this region where photons are scattering back when they come from infinity, so to say. Then there is, of course, you can calculate also the orbits or closest approach. This is your inner or closed orbit. This is outer closed orbit, stable closed orbit. You can calculate where you can have a photon orbit which is stable and closest to the black hole, where you can have an orbit which is again stable but farther from the black hole. You can compute and determine these. For example, you can find bounds, okay? You can set bounds. As I was mentioning, there was this shadow. You can calculate also shadow for this model, where there is this range of shadow radius with respect to the model parameter. There is this 1 sigma domain, 2 sigma domain, etc. For this model. Again, for a different range, you have these values, as you see. And in each case, you are computing and predicting a number depending on where you are in the parameter domain. Our idea is to test the model, and that's our main goal. For example, here you can have the bending of the light. Bending of the light involves a bending angle alpha. This bending angle alpha depends on the impact parameter B. For different values of the model parameter, we are having different predictions for the bending angle, and this again we tested with the observations. So we are looking at light. It's bending from this black hole, and looking at this black bending angle, we are able to say something about the underlying model or underlying prediction. The light, again, as I was telling you, there is this Hawking temperature. Hawking temperature, again, depends on the charge of the black hole. This is a different study, a little bit different study. But in this case, as you see, depending on the charge, amount of charge on the black hole, you have black, red, green, and blue curves. In each case, your Hawking temperature is taking different forms as you go along the radial axis. Yes. Also, the main point here is that you are having a black hole, and our goal at this point. I mean, maybe one of the critical things we will do with this black hole thing is that we will look at the radiation emitted from the black hole. The red arrows correspond to usual light emission, neutrino emission, the particles you know. But there are these black arrows here. The black arrows are something like they correspond to new particles that you don't know. I mean, normally you don't see these particles, but they can exist according to this model. So you can look at this black hole if there are such particles. And to do that, what we will do is to compute the Hawking radiation from this black hole by taking into account all these details, all these model details, and then collect the results to see if the evaporation rate of the black hole is large or small, or how the black hole evaporation rate depends on the number of particles and in a given range. From that, we will be able to conclude if there are particles in this universe which are not interacting with us, if there are such additional particles. For example, dark matter is such an elusive particle. We don't see dark matter in direct search experiments. All the experiments have failed. But when we look at light curves around the galaxies, when we look at structure formation, when we look at gravitational lensing around the black holes or other big astrophysical objects, we see that there should be dark matter there. Gravitational indication is there. But we don't have direct observation. It looks like, it turns out that, at least this is our conclusion, it looks like dark matter is not interacting with us through electromagnetic, weak, or strong interactions. It doesn't see us, and we don't see dark matter. But it interacts with gravity, and it's there, always there. Okay? So,
I think we can do a Q&A.
if you have questions, I try to keep it short because this is night time. Otherwise, I would have zillion different slides. Okay, I have a completely different model which I am investigating with Reyhan Hoca, and she knows these details, but I had to cut it short. Yes.
Thank you for your. You showed us pictures of Sagittarius black hole, I suppose, and then Sagittarius black hole, I suppose, if I'm not mistaken, and then you compare it from AI.
Yeah.
Yeah.
No, I didn't do that.
I worked out that. Yeah. My question is, so you said that those lights, like those bright areas, are matter rotating around the black holes?
No, there is this black hole and there is this matter coming from some other galaxy or somewhere. It's accreting. It's flowing near the black hole. Some of them having zero angular momentum just fall upon the black hole. But those having large enough angular momentum revolve around the black hole, and we see light coming from them. So,
My
yeah.
question is, like, I expect a scenario that brightness will be like scattered uniform, but it was not symmetric. So in some parts, when you see
Because the
bright-
black hole is a rotating black hole there. Therefore, there is a symmetry axis, rotation axis, and the figure is not symmetric. There is a certain distortion. But I was discussing with you here was non-rotating, non-charged. Let's see, just simple black hole, because just I wanted to explain you basics. Therefore, I didn't go into those details. But normally, this black hole M87 star and Sagittarius A star, they are rotating, spinning black holes. We know this. Therefore, thank you very much for your careful question. Yeah. Distortion is different.
When you're talking about the entropy, you mentioned that the area is important rather than the volume.
Yeah, important.
I couldn't understand exactly what do you mean by area and the volume, because actually what you described is like a fabric and there is something very messy. Yes, curvature.
Yeah.
What do you mean exactly by area? Like the outer circular thing? And if it is like that, what do you mean by the volume exactly? And
Well, there is a black hole and there is a horizon, which is the point of no return. How close there you go, you are finished. The point is that using this horizon radius, we can define a volume. Okay, this in this symmetrical, non-rotating for black hole, it is just the volume of the sphere.
like a conic or somehow.
No, that's the gravity. I mean, when we can define a volume for this structure. We can say that given the horizon radius, it is something 4/3 pi times r horizon cubed, usual volume. The point is that we are, for example, we are taking, could you imagine, we are taking, for example, Britannica encyclopedia, okay, flow number chart, we throw it in towards the black hole, it gets lost. What happened to knowledge? What happened to information? Yes, this is known as information paradox. I mean, there's nothing. You lost completely information. There is an asymmetry in space. In this sense, you have to understand what is happening in the black hole. What is happening in the black hole states? How is this information lost? You gotta understand all these things. But the point is that in this matter, when you throw these things, I mean, number of microstates are increasing, huh? So you have a black hole having a more and more number of microstates. For example, this room is full of gas molecules, and each molecule can have infinite different positions. And if we take into account all possible configurations of air molecules in this room, and if we take its logarithm, we find entropy in the room up to Boltzmann's constant. Huh? That's the calculation of the number of microstates. Imagine a black hole. In the black hole, again, you have number of microstates within the volume. But entropy is not proportional to volume. It's proportional to the surface area. I mean, what contributes to entropy is not the volumetric states. What contributes to entropy are just surface states. It is the way it is giving information to you. Of course, people have discussed this information paradox for a long time, but last summer there was a conference there. In that conference, there was this guy, Edward Witten. And Witten was giving a different calculation of this entropy thing. And he said that, no, entropy is not, absolute. Entanglement, quantum entanglement is not in the black hole. It's black hole and the surrounding space. And somehow he killed many papers of people by that simple work. He's a smart guy and he knows
I have a question.
Yes.
I don't know the history. Was it like this first they anticipated that there should be black holes, and then eventually they got the evidence?
Yeah.
Or was it just about the dark matter? That's what.
No, it was in 1780s, in the previous century. Some guy theorized that there should be black stars. He said that there should be objects whose escape velocity is greater than speed of light at that time. I mean, more than 200 years ago. And people at that time didn't show any interest. In 1800s as well, this topic evolved in the same way. Last year, one guy got Nobel Prize, okay, a mathematician, not a physicist. A mathematician got physics Nobel.
It was forbidden, but he didn't do mathematics.
Yeah, because this guy was almost giving up on his PhD, but he barely finished PhD with his, advisor, whatever. And he started working on this problem. He has shown by some crazy mathematical details and theorems that in Einstein's theory, there must exist singularity. Singularity means black hole, because there is a huge, infinite curvature point. So this is a singularity. He said that it doesn't matter if you are looking at localized objects like black holes, or if you are looking at universe as a whole, there must exist singularity. And these theorems, these Penrose theorems, or Hawking-Penrose theorems, lived for decades and decades. But once they observed black holes, once they took the picture, they understood that black holes do exist. And they looked at the literature and they saw that, yeah, a guy predicted them by writing down a mathematical theorem. So a mathematician got Nobel Prize for this reason. Even the guy himself didn't expect such a thing to happen. What happened? And so, black holes were expected well before Einstein. But there were people who, calculated, predicted all these details within Einstein's theory. And they said that there are similarities in this theory. You cannot avoid them. And after the observation, of course, it was confirmed.
So, for instance, for a layman like me, how many black holes by number did they take a picture of? Does it make any sense?
Don't know that detail. By number, you mean number of black holes?
For instance, Sagittarius was one example. So, like they say, 50 different black holes.
I got it, I think. Essentially, we expect to see a black hole at the centers of each, let's say, galaxy. Because galaxies started from nucleation of this hot matter at the very beginning. The cold parts have turned into these, the solar system-like structures. But at the center, there is a hot, let's say, origin domain, which we expect to be a black hole. I don't know if there is such a theorem, but normally, physically, we would expect such. For example, Sagittarius is the black hole in our Milky Way.
Okay.
Yeah, it's at the center of our Milky Way. And 87 is at the center of the neighboring galaxy. And I'm sure they will observe, they are observing many galaxies. There is this new telescope, James Webb telescope. It is also taking pictures of very early galaxies in the early universe. There are not galaxies and even black holes. They say that that object is black hole or galaxy, whatever. Yes.
I wonder, how do we understand the formation of supermassive black holes? Because how can those systems get that massive? Because they don't seem to come from star evolution. How do we understand that scale?
Yeah, this is a very good question. If I ask myself, I also don't know the exact answer to this question. But I think things are hidden in the galactic dynamics. These supermassive black holes are at the centers of the galaxies, at the hearts of the galaxies, where there is a huge matter distribution. And I think at their centers, we have such domains, such regions, huge matter concentration. That's what I can say.
And does it make sense that they have managed to form within the age of this universe?
I mean, they should have managed as far as we observe. But,
Yeah.
but I think, I mean, this question has many dimensions. For example, dark matter. JWST started observing very early galaxies. Normally, dark matter helps formation of galaxies, but that's a very slow process. Slowly and slowly. Dark matter cannot do any fast black hole formation. It cannot do that. But they observe something like 13.5 billion year old galaxy, which is huge. This means that there could be something strange with dark matter approach, perhaps. Perhaps that approach will change our picture of the galactic formation. Perhaps that will explain how these supermassive black holes remain in this form. But I don't know the answer. My answer may not be the answer. Questions? I hope it was clear. I'm sorry. Nighttime, it was a little bit a heavy topic, but anyways, thank you for your patience.
Thank you all for coming.
Evet.